Insert in heap. How do you insert a new element into a heap? This is always done at the end of a heap. That is, whenever you want to insert a new element, insertion is always done at the end of a heap. So if this is your heap and you want to insert a new element, you'll always insert it here. That is, wherever is the end of the present heap. But after you do this insertion, this may violate the heap property. So your heap may no longer remain to be a heap after your insertion. So the procedure that you have to do in order to re-heapify, that is what we are going to learn in this lecture. So let us understand this. You already added at the end. After this, what you have to do, you have to find out the parent of this node. How do you find the parent of this node? Because we are using the array representation, you can directly find the parent using the formula I minus 1 divided by 2 and then take the float. If you use this formula, you can directly find the parent of any node. So let us just check this out. 0, 1, 2, 3, 4, 5. These are the indices in case you are using array representation. So what is the parent of 5? You have to do 5 minus 1 by 2 and then take the floor of it. What is 5 minus 1? It is 4. 4 by 2 is 2. Floor of 2 is 2, which says parent of 5 is 2, which is correct. 2 is the parent of 5. So in any heap, you can use this formula in order to identify the parent of any node. So here, first thing you have to do is to identify the parent and then you have to heapify. But the point is, in the heapify algorithm that we already learned, we always moved downwards. That is, the heapify was always proceeding downwards. And here you are already at the leaf. So you have to move upwards. For this, you use something called heapify up, also called as bubble up. So in this procedure, whenever you do heapify up on any leaf node which is violating the heap property, that is the whole complete tree should be fine other than this newly added leaf. So in that case, when you do bubble up on that single node, you will be able to restore the heap property of your complete heap. So this is what you're going to do. How do you do bubble up? You see the parent of this node, then you check whether parent is larger or this node is larger. So in case the leaf node is larger, that is the child is larger, then you don't have to do anything. In case child is smaller, here we are considering max heap. So if you are considering min heap, you want to build a min heap, you have to consider opposite of whatever we are saying. That is, if we are saying larger, you have to consider smaller. We are always looking at max heap. Throughout our lectures, we'll only do max heap. Okay, that is to avoid confusion. So you have to see whether child is larger or parent is larger. So if already parent is larger, there is nothing to be done. Your node is at correct position. You can stop there. But if the parent is larger, you have to swap both these nodes. So you have to swap the node at position 2 and position 5, which means this value will now come up here. After this, you have to continue this bubble up till the point it stops. So when will it stop? It will stop either when the bubble reaches on the root or when you reach a point where the parent is already larger. That is when you have to stop. So now you compare this node with its parent. And when you compare, in case parent is larger, it is fine. If the child is larger, then you have to do a swap. This is the algorithm that we are going to follow. What we'll do, we'll understand this with an example, so that will be easier for you to grasp. So we'll use this heap. 80 is the root. 80 has two children, 74 and 32. 74 again has two children, 63 and 50. 32 also has two children, 15 and 21. So if you see this is already a heap. It is following max heap properties. 80 is larger than 74 and 32. That is following 74 is larger than 63 and 50. Similarly, 32 is also larger than 15 and 21. So this is a max heap. Let us say I want to add a new value, 85. I want to add 85. Where will I add? I'll add as the last element of the heap. So here I have to add 85. After I added 85, 85 here violates the heap property. So this is no longer a heap. How do I restore? I do this bubble up operation or the heapify up operation. I'll check 85 with the parent, which is 63. Which is larger? 85 is larger. So if the child is larger, I have to swap. I'll swap 85 with 63. 85 will come here, 63 will come here. What is the next step? I have to check 85 with its parent, which is 74. Which is larger? Still 85 is larger. So I have to again swap. 74 will come here, 85 will go upwards. What is the next step? Again consider 85 with its parent, which is 80. Which is larger, 80 or 85? 85 is larger. So again you have to swap. 80 comes here, 85 goes on to the root. So whenever it reaches root or it reaches a position where parent is already larger, you can stop the algorithm. So at this point 85 has reached the root, which means this is following heap property. So here if you see 85 is larger than 80 and 32, 80 is larger than 74 and 50, 32 is larger than 15 and 21, 74 is larger than 63. So this is following heap property. So this is a max heap. So you have successfully inserted. Next thing is we'll look at the algorithm and we'll understand what is the pseudocode. Let us write the pseudocode for this. So then it will be very clear for you. How do you write the pseudocode? You should first have the logic clear. What do you have to do? You have to append the new value into the heap. After that, you have to do the heapify up procedure. That is, you have to check with the parent, check whether parent is larger or the child is larger. If the parent is larger, it's fine. If the child is larger, you have to swap the parent and child. So this is the algorithm. So let us write the pseudocode for insertion in a heap. So this is the algorithm. Insert. You have a heap and you have a new value that is to be inserted. So I'll call value. This new value you have to insert into the heap. So heap is having array representation. So I'll use array. So we are using array representation for representing heap. So on this array, on this heap, I have to append the new value. So this array, I'm going to append the new value. So whatever is that value, I have to add as the last element of the array. After this, what do I have to do? I have to start heapify up from the newly added value. Where is that newly added value? At the end of the array. So my I is equal to length of my array minus 1. So this is the last index of the array. That is where we have newly added the element. After this, we have to do the heapify up procedure. So while you can continue this till I reaches the root. So I greater than 0 till this point. Or you have to break in between if parent is already larger. So that we'll do inside this while loop. So here what do you have to do? You have to first identify the parent. Parent is, what is the value of parent? I minus 1 by 2. This is the index at which parent is present. So you have to find the index of parent from here. Then you have to compare the parent with the node that is at I. So if the heap of I, the value at index I, if this is larger than the value at parent, in this case, what you have to do? You have to do a swap. So you have to swap which values? Array of I, that is the heap value at ith index, and the array of parent. So you are swapping parent and child in case child is larger. And then what do you have to do? You have to update I to parent. So in the next iteration of this loop, your I should be whatever is presently the parent. And if this is not hit, that is if the parent is already larger, then you can break so in case of else, you can directly break. You can come out of this loop. So this is the break. So this is the algorithm for insertion in a heap. What are you doing? You are appending the new value at the end of the array, that is end of the heap. Then you are going to the newly added value. You are starting from the finding the parent. Then you will check whether the parent is larger or the present value is larger. If parent is larger, you are breaking from here. If the present value is larger, you will swap with the parent and then change I to whatever is the parent. Then you again come to the next loop with the new I, that is with the parent's I. So what is the time complexity of this? Time complexity of this is depending on the height of the tree. Because what are you doing? You are having a heap, and whatever is the newly added value, you are propagating it upwards. So total number of steps is equal to the height of this heap. And what is the height of the heap? It is order of log n. So you know time complexity is order of log n. What is the space complexity? In this algorithm, we did not use any extra space. There is no recursion, no extra space used. There is only constant extra space for variables. So space complexity is order of 1. So for insertion in a heap, time complexity is order of log n, space complexity is order of 1.